Hi, everybody. Welcome to this talk about scaling out Spark in a different way we call serverless herd mode. So first, I want to talk a bit about Spark. Spark, as you know, has superpowers. On the one hand, you can process huge amounts of data with it. And on the second hand, which is great, you can easily scale it up by adding more nodes. So that's really awesome. But like every superhero, it has its weaknesses. And we really want to beware of the Spark kryptonite. So kryptonite number one is shuffle. Everybody's aware of shuffle. Shuffle is when the nodes have to exchange data over the network. And that's something to always be aware of. Kryptonite number two is skewed data. Skewed data is when you have lots of different tasks. Some of them are large and some of them are smaller because of the skewed data. And the small ones finish processing first and then have to wait for the longest task to finish. So that really creates processing delays and obviously extra costs because you have all these executors idling away, wasting your money. Okay, so kryptonite number three is the whole cluster model. Clusters are built for a reasonable load, and we need to basically select the cluster size. So for this particular amount of data, let's say this is the cluster sizing we select. As you can see, in some hours of the day, this cluster is over-provisioned. We have too much capacity for the data coming in. So that means that we have a lot of idle time, and that idle time translates to wasted money, basically, because we have idle resources idling away. The other problem is that when you do get that unexpected load, then the cluster sizing is too small for it. So then you end up having queues and longer wait time for processing of the data. So overall, you get excessive costs and you get delays. If we look on the other hand at the serverless approach says, let's spin up resources only when they're needed. And that means you only pay for the processing that's actually being done. So when you finish processing, you can tear down the resources and stop paying for them. The nice thing about it is when you do get that big burst of data, you could just spin up more resources and not have to wait longer for it to process. So you get no delays and it's very cost efficient. So in this talk, we want to tell you about a serverless approach for scaling out Spark, which we call Spark Serverless Herd Mode. We'll tell you about a real life case study of a system we've actually built to do this. And we'll tell you about some use cases to consider where you might, if you have some of them or something similar, you might want to consider such an approach yourself. Let me introduce ourselves. So I'm Ofer Dubrovsky, a big data dev lead at Nielsen Marketing Cloud. I love to focus on improving and tinkering with systems and constantly improve them. And with me is Eli Malka. Eli.
Hi guys, I'm Eli Malka. I'm a big data engineer. And for the recent 2 years, I work a lot with serverless. And from there, we took the concept of the solution that we are going to show you today.
So we are basically heavy Spark users. And in addition, we do a lot of serverless work. And we really, really wanted for a long time to marry the two approaches together. We finally did it, and this is what our talk is about. Okay, so to give you some context, I want to tell you what Nielsen Marketing Cloud is. Nielsen Marketing Cloud is part of the Nielsen Corporation. It's a product that's basically a DMP, data management platform used for marketing. It was acquired from a startup called Exalate in 2015. And we use this product to build marketing segments, which can then be used to run campaigns on ad networks and build device graphs. So this is really useful for targeting and business decisions. To tell you a bit about how much data we run, we're all cloud native. We're heavy users of Spark. We love Spark. We run a lot of Spark in the old cluster model way. Roughly, we run about 6,000 nodes every day. We process about 60 terabytes a day of new data every day. And all in all, we store about 5 petabytes of it. The system we're going to talk about is called Data Out. So this system is in charge of taking all this marketing segmentation data and uploading it to our ad platform partners. So in order for people to use them and run campaigns, they need to go to one of our ad platform partners and then select the segments they want to use and target them with ads. The system on its heaviest day ever ran about 250 billion events on that day, and it's running all on serverless. We did recently a video with on this system with AWS, Amazon Web Services. It's a great video to give you an overall view of what this system does. So if you're interested, go watch it. I encourage you to do so. It's on bit.ly, TMA-serverless. You can see the link below. Okay, so some numbers about this data platform. So as I said, top day ever, we ran 250 billion events. The events come in files. So we had about 17 million files to process, all in all about 55 terabytes of data. The other interesting thing about it is that the system scales up and down over the day. The peak hours in a normal day have about 6 terabytes of data, and the low hours have about 1 terabyte of data. So that's a big difference, and we really like our systems to scale up and down over time. As you can see, this is incredible power and scale. So we really needed good solutions for this. So let's look at the old architecture. Originally, this is how it was built. On the left, we have files coming in that need to get transformed. And we have about 140 platforms to send data to with about 600 accounts on them. Each one needs a different transformation. So we have lots of transformations to do. We were using a Spark cluster to do this part of the work. The Spark cluster would transform the data and send the output files to a S3 bucket where they would be stored. And then on the right, we have Lambda functions that would actually pick up one or more files and send to the right ad platform for each file. You can notice that on the left, the transform side with Spark was running the cluster model, and the right side with the Lambda functions was actually, it's pure serverless. So it was like scaling up and down over the day as the work came in. So this part really troubled us. We really wanted to have a seamless serverless model for everything. And for a long time, we were really looking for a way to merge these two different approaches. When we looked at the Spark cluster, we saw that basically the throughput or the efficiency of the cluster went down as we increased the size of it and added instances. So you can see on the left side, when we had a few instances in the cluster, we had a pretty good throughput. But by the time you get to 14 instances, the throughput dropped by about 35%. So that means each instance processes about 25% less data. When we got to about 40 instances, the drop was even more significant, was down to about 60% drop. So this was not great. And every time we had a burst, this was a big challenge for us. You can see that the sweet spot was around up to 10 instances. So as long as we kept the cluster at around up to 10 instances, it was okay. So originally our solution was to basically make sure the system and architect it in a way that we can run multiple clusters. And every time we would get a burst, we would spin up more Spark clusters and run them in parallel. So we could run 1, 2, 3 clusters, even more. And we made sure that each one is isolated and doesn't mess up the work of the other clusters. But this really bugged us. We didn't really like the solution. It worked quite well, but it was not elegant. So for a long time, we really wanted to do something better. And when we had the time to do it, we sat down to think of how can we improve this solution. So we decided to look for a better solution. And we set out some goals for that. So goal number 1 was it had to scale well. We wanted it to scale up and down really quickly, both to save on the cost as well as be able to handle the burst. Second, it had to be really efficient, and we wanted to pay only for the processing times that we do, but also that the total cost would be reasonable. And then the last thing, as I mentioned before, it needed to be able to handle burst really well in a timely manner. If you think about it, this is really a serverless-like system. Okay, so back to the architecture, we really wanted to take this Spark cluster on the left and then replace it with something better. But it took us a while to figure out what it should be. So to tell you all about it, I'm going to call Eli, and he'll explain the gory details. Eli?
Thank you, Ofer. So let's see what is serverless third mode and which benefits it can bring you. So the main point is that instead of running a Spark cluster, we run multiple isolated standalone Spark pods. And each Spark pod is independent of the other, which means that in this solution, we don't have shuffle. We have a task queue, and each Spark pod fetches a task from the task queue and processes it. And when it finishes, it fetches the next available task. Now, the cool part in this solution is that it can scale up and down according to demand. When we have more tasks in the task queue, we can spin up more Spark pods. And when we have less tasks in the task queue, we can remove Spark pods. Let's see how we did it. So the task queue is SQS, which is a queue service by Amazon. And we have a work manager that's responsible for preparing those tasks. And he prepares them in a way that each task contains the proper amount of data to be processed in a single Spark pod. Now, we are running this solution over EKS, which is Managed Kubernetes Service by Amazon. And every few pods are running on EC2 machine. And we have two levels of scalability. The first level of scalability is using horizontal pod autoscaler, or HPA, that's responsible for adding and removing Spark pods. The HPA is monitoring the number of tasks that we have in the task queue and decide accordingly how many tasks we need to have. The second level of scalability is using cluster autoscaler, which is responsible for adding and removing EC2 machines in order to fit all our Spark pods on the EKS cluster. So notice that this solution is very similar to the serverless concept because we are getting computation power according to the amount of work that we need to do. And when we finish this work, we tear down all the no longer necessary resources. Do you remember kryptonite number 1, shuffle? In this solution, we don't have shuffle. Since every pod is isolated and running standalone Spark, we don't have shuffle at all. And regarding kryptonite number 2, skew data, we still have skew data because this is the nature of the data in our system. But now it doesn't have any effect on the system. Since every pod is isolated, we don't need to wait for the slowest executor to finish the work. We can start a new task immediately and not having idle times. Now let's see the results. This is the scalability of the system in action. At the top graph, you can see the number of tasks. And at the bottom graph, you can see the Spark pods and EC2 machines. So you can see that those two graphs are moving together very closely. When we have more data came into our system, we spin up more Spark pods and EC2 machines. And when we get less data into the system, we remove Spark pods and EC2 machines. So we are scaling according to demand. Now let's see what happened when we have bursts. At the top graph, you can see that the number of messages goes between 20 and 60. This is the normal load of the system. And now take a look. A huge data burst coming into our system, and the system immediately responds by scaling up and start dealing with the queue. Do you remember the 3 goals that we set in mind to do? We do all 3 of them. We scale up and down according to demand. We pay for what we use because we remove the resources that we don't need, and we can handle bursts. Now let's take a look at the performance of the system. As we add more and more instances, the number of megabytes we process per instance per hour remains very flat. This is exactly the linear behavior that we wish to have. Do you remember how it was with the old solution? As we added more and more instances, the efficiency went down. And you can see that the new solution all across the board is better than the old one. For example, if we will take a look at 10 instances, we have an improvement of 128%. Also, do you remember where was the sweet spot? It was right here. So even in the sweet spot, the new solution is better. Now let's talk about money. This is a cost comparison between the old system on the left and the new system on the right. In the old system, the cost was very fixed because we were paying for a cluster with fixed amount of instances that were running 24/7. But in the new solution, the cost is changing every day according to the amount of data that we need to process that day. And of course, the new solution is cheaper. This is all the savings. This is actually 55% of saving, which in our case was $15,000 per year. Now let's look a bit under the hood to see some extra stuff that might be interesting for you. We are using Instance Fleet. Those are the free instances that we are using. Those instances are similar in cost to the instances that we were using in the old system. And each instance has 8 cores and 32 GB of memory, and we can squeeze up to 5 Spark pods on each instance. And we give each Spark pod 5 GB of memory. And in this Spark config, we can see that we are running one executor with 1 core and 2 GB of memory, and that this is standalone Spark. So by looking at those numbers, we can understand that the door is open for more optimizations. For example, we can add more memory for each Spark pod or squeeze more pods on each instance, and we are going to play with it in the future. Do you remember that we are using horizontal pod autoscaler in order to spin up and down the Spark pods? Now let's understand how it works. So this is the formula that we are using in order to determine how many pods we want to have. We divide the number of tasks in the queue by 2. Let's see a simple illustration. We have 4 tasks in the task queue, so the desired pod is 2. Now let's assume we have 1 pod currently running, but we want to have 2. Then we just need to spin up another pod. And the reason that we are dividing by 2 is that each task won't wait longer than 2 processing cycles. Now, scaling down is dangerous. Let's understand why. Let's assume the desired pod is 2, and the current pods are 4, so we need to remove 2 pods. The problem is that it is possible that we will remove a pod while he is processing a task. So the task will be stopped in the middle of the work, and we will have lost tasks. We actually suffered from this problem, and we had 240 lost tasks every day, which translate to lost processing hours and reprocessing of those lost tasks. So obviously, we had to find a way to overcome this issue. And we found a way to do graceful termination of the pods. So instead of killing the pod immediately, we found a way to let the pod finish processing the current task and then terminates. Let's see how we did it. So let's assume Kubernetes needs to terminate pod number 2. Then Kubernetes will send a prepare to die signal and then waits until he gets back a ready to die signal from the pod. Let's see how we did it. We had to change 2 places, one in our application code, and second in Kubernetes pod lifecycle. I'm not going to go over all the code because we don't have enough time, but the main point is that we override the pre-stop command of the pod lifecycle, so it will send a signal to the application and then waits until the application returns back a message, which means that it's done processing the current task, and then we can terminate the pod. We can also access the Spark UI of the live spots. In this dashboard, every box is a Spark pod that's running right now, and by clicking on the URL, we can access the Spark UI of this live pod. Now we are going to talk about some cool use cases where our solution is good for, and for that, I'm going to hand it over to Ofer.
All right, thank you, Eli. So let's talk about a few use cases to see what this is really good for. So use case number 1 is machine learning classification of pipelines of videos, images, and maybe sound clips. So usually these come in at varying rates over the day. Maybe in the middle of the day, you might have more, and at nighttime less. So you really want to have a system that can scale up and down with the traffic coming in. So this system is perfect to do classification of these events coming in or files. The nice thing about it, not only do you save money, but when you do get that big burst of data, you can guarantee that you can process it really quickly and classify it quickly. So another use case is bursty data pipelines. This is basically the use case we talked about. This is great when you have pipelines that have different bursts and varying amounts of data coming in, or that have very skewed data. So this solution is perfect for that as well. And a third use case we want to highlight is basically machine learning training, where you have very large divisible data sets. So an example of something like this is maybe you have to train on millions and millions of images. So the common best practice is to divide up the image base into lots of smaller image bases and do the training separately on separate machines or clusters. So this is perfect for our system as well, because the system can scale up and down with the amount of data coming in. Again, a perfect solution. I want to summarize what you've seen. So we talked about a system of Spark that we call Spark Serverless Herd. It's a system that's very much serverless-like. It has the ability to handle huge amounts of burst and scale up and down with the traffic as it comes in. And what's nice about it, it's very cost effective. So not only can you process data faster, you do it at a much cheaper cost. We really encourage you to consider trying out this methodology. And if you have interesting new use cases, send us a note. We'd love to hear about it. I want to remind you to fill out the feedback for our talk. So don't forget to rate and review the session. And in case you want to get in touch with us, both Eli and I are on LinkedIn. I want to remind you to watch the video about the data out system. Again, it's on bit.ly/TMA-serverless. The link is on the slide. And if you want to read our blog, the link is on the slide below. Thank you, guys, and thank you for coming to our talk.